Okay, so we are ready to continue. The next speaker is Ioannis Dalianis, and he's talking about the vacuum structure of the N equals 4 conformal supergravity. Please.
Okay. Thank you for the introduction, and also thanks Corfu Summer Institute for the opportunity they gave me to give this talk, entitled Vacuum Structure of the N equal 4 Conformal Supergravity. This is a work in progress, which is done in collaboration with Alex Karagiannis, Georgios Tringas, and Ioannis from NTUA. And me, I'm Ioannis from the University of Athens. So we're going to talk about conformal supergravity. So let's start saying a few words about conformal gravity, just a small overview. Conformal gravity in 4 dimensions has an action given by the square of the Wild tensor. So this is the action. And this action has an exact symmetry under Wild transformations of the metric of this form. So this theory, in contrast to Einstein theory, where the action is described by the Einstein-Hilbert term, it's sensitive to angles, but not to distances. But it's interesting, but this theory has been considered as a possible UV completion of gravity. And also it has emerged from twistor or string theory, according to a result from Berkovits and Witten. And the main disadvantage of this theory is that it has ghosts, due to the fact that the equations of motion are of 4th order. So since gravity is an example of derivative theory, the ghosts of this modified theory of gravity are considered to be physical excitations. So, and this is the main advantage. So either you have to abandon unitarity in this class of theories that contain ghosts, or you have to accept that the energy eigenvalues of the ghosts are negative. So in the first case, this is very bad news for the case you want to quantize the theory because you have negative norm states. In the second, you have to accept that the energy is unbounded from below, so you have instabilities. So some people claim that ghosts might not be problematic if the ghost is somehow isolated from the theory, so decoupled from the rest of the fields. And another option is to make them heavy and integrate them out. On the other hand, the advantage of this theory, of higher derivatives, is that the quantized version of the theory is much more convergent and renormalizable due to the good features of the propagator that follows rapidly in the UV. So let's now turn to conformal supergravity, which is the topic we examined. So apparently, is a supersymmetric completion of the Weyl gravity described by the Weyl square term. So conformal supergravity is invariant under the full superconformal group, and let's recall that the superconformal group contains the standard generators of the conformal group, which is the rotations, the dilatations, the translations, and the conformal boosts, as well as the usual Q and special S supersymmetry. So what is an important remark is that the N has to be less than 4 or equal to 4. Otherwise, conformal supergravities cannot exist of cell, and the theory will contain higher spin fields. And this is a result from De Witt and Ferrara from 1979. So in this work, I will focus on the N equal 4 conformal supergravity, and I will explain why in the following slides. So now let's say a few words about the fields of conformal supergravity. Notice that in conformal supergravity, we have fewer fields than the corresponding conformal gravity multiplet, and this is due to the high degree of symmetry, which implies that certain modes should be absent. And also that 4-dimensional conformal supergravity actions were known for a long time only for N less than 4. The N equal 4 supergravity has been constructed, the full of-cell action has been constructed only very recently by the papers of these people, the Jerry, Sahu, Buscher, De Witt, as you see a few years ago. Also, Chaitlin and Kuzenko and Buchbinder proposed another way to find the bosonic sector of this action, of this theory, by utilizing the conformal anomaly of the n equal 4 vector multiplets. So, as well, conformal supergravity has been obtained as the massless limit of this theory, as you see is the Weyl square term plus the Einstein-Hilbert term here. And in this limit, the spectrum of theory is reorganized, so it's enhanced from super Poincare to super conformal, and the R symmetry is promoted to gauge symmetry. And also, it has been noticed that also in supergravity is expected to have ghost propagating states. However, as I said, this theory, the conformal supergravity, there's still good motivation to study it because, among other reasons, it emerges from string theory. So why do we study, why I'm talking about n equal 4 conformal supergravity? Why are we interested in this class of theories? We are interested in this class of theories because the n equal 4 conformal supergravity has an ambiguity. And this ambiguity is due to this holomorphic function h that appears in front of the Weyl square term. And this h function is a function of the fields phi, which parameterize the coset space as u1.1 over u1. So the existence of this ambiguity was known for a long time, since 1982, but it has been explicitly worked out only recently in 2020 and 17. So what is this ambiguity? Okay, I would say later, but let me say in advance that this ambiguity is that you have solutions that this function cannot be specified. And I will say more details in the next slides. So now turning to the fields. The fields of this theory are the field bind, the SU4 fields, the gauge field, the spin connection, the conformal boost, and we have also the T field, which is the self-dual in SU4, the E field, which is important for the later discussion, the D and the phi field that, as I said before, it parameterizes the coset space. So in red here is the E and phi field that we will focus on. As well, we have the fermionic sector, and the source transformation of these fields can be found in this reference here. So now let's turn to the action. As you expect, the action of the conformal supergravity contains the Weyl square term. And as I said before, there is this holomorphic function, this coefficient in front of the Weyl square that introduces the ambiguity that I talked about. So the field of cell action has been, as I said, constructed in 2017. And for vanishing field values, the fields are here, T, E, and F, and phi, and D, sorry. We get the creation of motions. So this is the Bach tensor, and this equation of motion is found after varying the action with respect to the metric. So the Bach tensor is given by this equation here. It has this form, and it has to be contrasted with the Einstein tensor. And notice that the Bach tensor is any metric contraction of this metric is 0, so it's traceless. And this is this fact is the reason that conformal supergravity cannot give us information about distortions of distances and volumes, but only of angles. So, in other words, shapes. So, this equation of motion for vanishing fields give us the solutions are conformally flat backgrounds. So, the problem with this solution is that these are indistinguishable in the Weyl theory because they are all maximally symmetric with the vanishing Weyl tensor. In other words, we can, with conformal transformation, we can go from one space-time to the other. So our aim in this work, in our research, is to uncover part of the vacuum structure of the n equal 4 conformal supergravity by exciting some of the scalars. Okay, here I have added a side remark, let's say a slide that is outside conformal supergravity. I added this for the audience who may not be familiar with unequal for conformal supergravity, but they are more familiar with some cosmological aspects of supergravity. And I wrote here the Lagrangian of a higher curvature supergravity, R plus R squared. This is the curvature superfield. And this is a well-known example because the bosonic sector of this theory gives the famous Tarobinski-like plateau potential that can give viable inflation. So several years ago, we studied with these people some modification of this function up here that violates our symmetry. And what we found that when you violate our symmetry, a new vacuum structure is found. And this vacuum structure contains extra minima that breaks supersymmetry. And of course, they break our symmetry. And also, you find new features with Tarobinski-like plateau potentials. So something similar, we'll do it here, but for the conformal supergravity. And what we do is we excite the scalars E and phi. Notice that we cannot excite other fields, for example, the T, because we reduce the background symmetry because of this. It has also this AB indices, which are in the indices of the tangent space. So in order to study the vacuum structure, we have to study the Lagrangian, and this is the Lagrangian of our theory. The next step we do is we then grade out the D fields, which are auxiliary, and in red is let's say, the master equation of our theory. So in this master equation, you see the Weyl square term, it's a conformal gravity, and the terms that depend on the E field, and as well as the H field, which is the holomorphic functions that introduce the ambiguity of n equal 4 supergravity. And please also note here, that another disadvantage of the, let's say, drawback of this theory is that it appears here the Ricci scalar who have the E field which is conformally coupled, and the sign is wrong. The sign is minus, which means that this theory in the infrared, in order to be attractive, we have to introduce vector multiplets coupled to supergravity in order to make it attractive. But in the UV, the theory behaves very well. So the comment is that this theory has to be in the infrared, has to needs to be completed with some extra fields, matter fields. So we're interested for maximally symmetric vacuum solutions, which are Minkowski, de Sitter, or ADS and de Sitter. And this means that the answers for the Riemann curvature, Riemann tensor is this one. So here, lambda is the cosmological constant. Of course, you know that positive is de Sitter, 0 is Minkowski, negative is ADS and de Sitter. And we also excite the fields epsilon, E and phi that we assume to be constant but not 0. So now the equation of motion that we get have this form. As you see here is the Bach tensor. Now we have new terms. Here, for example, you have this is the Einstein tensor. And also have new functions labeled A that depends on the holomorphic functions H, and the C that also depends on the fields E, and we have the potential V. So the form of the potential V is this one, and as you see here, the holomorphic function appears in two ways. One is as a function of derivatives of these functions, and what we find from the equations of motion is firstly that we identify the cosmological constant that has this form. And also we find that the second equation, this one, we can recast it in this form. And this equation is satisfied at the critical points of a function, which is defined as the ratio of the potential over the function c squared that I defined in previous slides. And this function, we call it V effective. So for extremizing the V effective, we will find the solution of these equations. And also we find the minima of the conformal of the potential of the conformal supergravity. So the V effective has this form. And let me also add that in order to proceed with the calculations, it appears to be convenient to change coordinates in the phi field and parameterize the fields that parameterize the coset space and introduce the S field. And so now the H function becomes a function of the S fields. Okay, and we proceed by making some answers about the form of the scalar E. And we start with the simplest answer, which is to take the E to be a diagonal matrix. And working out the theory and finding the minima, we find that the cosmological constant for this answer has this value given by this expression. As you see, it can be either negative or positive. And without entering into details, let me show you how do we classify our solutions. This is a classification for this ansatz to have a diagonal E matrix. So we find the Sitter, Minkowski, and ADS vacua. And this is the value of the cosmological constant. As you see, depends on the verb of the E field, the scalar. Okay, these are also solutions that are found numerically after solving, after finding the extrema of the effective potential. And whether you have the background is DS, ADS, or Minkowski depends on the number of zero eigenvalues you have in the matrix E. Of course, there are also other answers one can make for the E matrix, the scalar A, to be, for example, block diagonal or to be generic. For this case, which is easier to compute numerically, we also find two different vacua with ADS vacuum, but with different value of the cosmological constant due to the presence of these non-diagonal terms. We also have done computations for this 3 times 3 diagonal and 4 by 4, but it's much more cumbersome to find results, and the expressions are much more complicated, so I do not quote them here in this talk. So far, we assume that the holomorphic function is constant. If we assume that a non-constant holomorphic function, then in the effective potential, a new term appears, and it's this one. So that's why we label the first term constant for constant holomorphic function, and VDH, okay, that just to underline that and highlight that the derivative of the holomorphic function is not constant, is not zero, sorry. So in this case, we derive this expression for the value of the cosmological constant, and as you see, it depends on the V constant and the new term here. Thanks. What is of special interest is that whenever you have zero eigenvalues, then this extra contribution goes to zero. And this is really interesting and, let's say, important for our calculations result, because if we assume a general form for the holomorphic function H, this may not complicate our analysis, and we can easily find the result for the cosmological constant if the matrix of the scalar field E has a zero eigenvalue. So this is a very helpful observation. So now, considering non-constant holomorphic function and assuming a diagonal E matrix, we get vacua that are classified in this table. So you see here different cases. For example, when we have when we don't have zero eigenvalues, we can have either the Sitter, Minkowski, or ADS vacua. The rest of the cases are all ADS, and this is the value of the cosmological constant. So now you see it also depends on the holomorphic field that is hidden inside the functions G and A. Now, let me also add some comments about the form of the holomorphic function H. So, as I said at the beginning of the talk, this function H is the reason that n equal 4 conformal supergravity has ambiguities. And one has to assume a specific form for the H function. However, not all possible forms are allowed. And the reason is that once you find the minima of this theory, of the effective potential, then this minima should lie inside the Poincare disk, because recall that S field parameterizes the coset space. So this is a constraint that all the examples about the possible form of the holomorphic function should satisfy. And let me show you here two examples. One is like this, one is this example. So you see a polynomial form. Then we find the ADS vacuum. And let's consider, let's say, quite more generic example, which is a monomial with n free parameter. Then we find the cosmological constant given by this expression. But what is important is that we find that the positive values for n are ruled out, because the solutions, when we extremize the potential, we find that the vacuum, the S value of the vacuum is outside the Poincare disk, so we don't consider them. On the other hand, we can consider only negative values for the power here. Okay, so this is a comment about the form of the holomorphic function. And finally, let me add a few remarks about the supersymmetry breaking in the vacua, because as I said, we studied the vacuum structure of the theory. So we have Q and S supersymmetry transformations, and these are generated by opposite chirality periods epsilon and eta. What we find is that the S supersymmetry is always broken since the gravitational shifts are non-zero for non-trivial eta chiral spinor. On the other hand, the Q might be preserved. So we did a survey, and we found that only Minkowski vacua preserve Q supersymmetry. Okay, so here are some conditions for unbroken Q supersymmetry. Okay, I think this is the important conclusion, is that only Minkowski spacetimes are supersymmetric in valid conformal supergravity. And finally, let me turn to my summary, which is my last slide. So in this work that we hope to be online soon, probably next week, we have studied the vacua of the maximally n=4 conformal supergravity, which is the supersymmetric completion of conformal gravity. And what we found is that this theory admits non-trivial ds, ads, and Minkowski vacua, which are determined by the vacuum excitation values of the scalar field E, as well as the field phi that is inside the holomorphic function H. S supersymmetry is always broken, while Q supersymmetry is reserved only on Minkowski backgrounds. And let me note that when you give a verb to the E fields, then you break both conformal and SU4 symmetry. But let's note as a final remark that in if you want one quantize the theory, then he expects that there is a superconformal anomaly. So you expect the conformal symmetry to be broken. I think that's what I want to say. And I thank you for your attention.
All right. Thank you very much for your nice and interesting talk. Questions?
One question combined into how many scalars in full dynamical scales in this theory, and what kind of kinetic term or coset they form in general?
And what kind of?
How many scalars?
Yes.
And what kind of nonlinear sigma model, which coset they define? Or
the phi fields define the coset space or parameterize the coset space. Sorry. As U1.1 over U1.
Scalars, but you have more.
Yeah, we also have the scalar E, which is in the 10 representation of SU4.
Am I correct? There are 10 physical scalars.
Mm-hmm.
And if I look at the full kinetic terms of these 10 scalars, what kind of nonlinear sigma model, what kind of coset do you have? Or maybe it depends upon H functions.
Okay, this is the Lagrangian. So here are the kinetic terms and interactions between the directions. Yeah. So the D field is auxiliary, so it's been graded out. So this is the, as I said, the master equation that we use to we follow to find the meaning of the theory and the dynamics of this theory.
Are there more questions?
Yeah. Okay, now comment something more. Okay, so just a short comment that, of course, in the vacua of this theory, we studied the stability of the theory in order to have positive masses and not tachyonic. And non-tachyonic masses can be found for ADS vacua.
Other questions? You want to take the questions from? No.
Okay.
Okay. If there are no more questions here, we thank you again.
I also thank you.
All right, so the next speaker is George Tringas from Athens, and he talks about from type 2 to 3D flux vacua on G2 orientifolds.
Hello. My name is George Tringas. I'm from Athens under the supervision of Alex Kehayas. And today I will try to outline some results that we found on these papers with Fotis Farakos, Thomas Van Riet, and Maxime Emelin and Fotis Farakos. So let me outline the talk. I will start with a very short introduction and motivation, and then we'll see the general action and setup. We'll talk about the internal space, seven-dimensional space, since we're looking for three-dimensional flux vacuum, the symmetries, the orbifolds, the allowed fluxes, and then in case of ADS, we will search for indications for scale separation, and then we will see if we are able to perform a de Sitter uplift. So the most well-known and probably prominent quantum gravity is string theory, which can be described in 10 or 11 by 10 or 11 supergravities. However, we experience 4 dimensions in our universe. Also, we don't see supersymmetry and the extra dimensions. Also, we know from cosmology that the cosmological constant is positive. So we have like a de Sitter vacua. So can string theory explain all this, explain the above? Actually, yes, if one start with a 10-dimensional action, try to compactify and look, for example, for the de Sitter vacuum, we'll find many problems, and even for the de Sitter solutions, anti-de Sitter solutions, that string theory is very rich. There are many problems regarding the hierarchy of scales and technicalities, and also with moduli stabilization. So a correct truncation from 10 dimensions or 11 dimensions down to 4 dimensions, for example, describe our universe doesn't mean that we have like a correct EFT. And this is a subject of the Swampland program, where people try to conjecture EFTs and distinguish those who have which are compatible with quantum gravity. How our research is related to the swampland. Actually, swampland doesn't constrain that you cannot have an EFT in 3 dimensions, but it cannot describe, of course, our universe. So in order to understand the properties and explore the swampland, we will compactify from 10 dimensions down to 3 dimensions in order to explore the swampland. Also, in 3 dimensions, supergravity theories are much simpler, and the vacua that we find can be tested. For example, the ADS, prosthetic ADS, with 2-dimensional CFTs that we know better than 3-dimensional CFTs. So in these projects, we looked for classical vacua. We don't consider quantum effects. Full moduli stabilization, supersymmetric or non-supersymmetric, maximally asymmetric vacua, a hierarchy of scales if it's possible, like an indication for scale separation, and we want our solutions to be in the regime of large volume and weak coupling, and then we check the possibility for the de Sitter uplift. So I will start with the general setup, which is the action of type 2 theories, and we also consider sources, and we keep only the metric part. So the metric assets is that we have a maximal symmetric space-time, and is direct product with 7-dimensional manifold, and we also don't consider warping. So you can see here from the line element that there are some free parameters alpha and beta that they will be fixed in order to have a canonically normalized effective field theory, and upsilon here stands for a 3D scalar field that which is like is the volume of the internal space extracted. Since we don't have warping, we can easily perform a dimensional reduction. Okay, from like 10 dimensions, and also another feature of our analysis and of most of the compactifications that include sources is the tactical cancellation. Basically, the Bianchi identities, the integrated Bianchi identities in the compact space, in our case the 7-dimensional compact space, the source is replaced. The source here, which is actually the current of the source, sorry, which is actually delta functions, is replaced by a smooth function, smooth form here, in order to cancel this term. So the integral of the Bianchi identity to be 0 here. I will say some words about the internal space. We'll check both type 2A and type 2B, and I think that for type 2B, I will not have time to say some stuff. So in our type 2A example, we consider Ricci flat internal space, and in type 2B, we consider non-Ricci flat. So we have a 7-dimensional manifold with a G2 structure, which is actually characterized by the following 3 form. And here, SI is like the 7 moduli of the internal space. So what we want to see is when the internal space is Ricci flat or not. And it can be seen, for example, from the covariance of the fundamental 3 form, which is 0 when this full torsion tensor is 0. And this full torsion tensor is a sum of P forms, which we actually call torsion classes, and correspond to the irreducible representation of G2. So in case when the full torsion tensor is not 0, we can have non-Ricci flat space, and especially these W's are for our case. There is like a more general expression for the curvature, and also here we can see that the fundamental 3 form is closed and co-closed, but in Ricci flat is not closed, but it is co-closed, and this is a very important thing, as we will see. So let's see first the type 2A example. As I said, we have a 7-dimensional manifold, and we choose to be a 7 tori with the following orbifold here. And actually, the fundamental freeform that we have is invariant under this orbifold. We also want to include the O planes in our searching for vacua. So you can see here the action of the O planes on the coordinates of the internal space. So what happens with supersymmetry? Because in type 2A we start with 32 supercharges. So the orbifold truncates the supercharges down 4, and then due to the O2, the supercharges are truncated down to 2. So we'll have an effective field theory in 3 dimensions with 2 supercharges, like a supergravity with 2 supercharges. We also want to include in our theory O6 planes, and this can be done and can be seen from the combination of the involutions of gamma of the orbifold and the O2 plane. And here in the graph, you can see the directions where the O6 planes are wrapped, while the directions with minus correspond to the directions where we have replaced the delta function with a smooth function. Let's see what is the allowed fluxes that we have in this theory. As I said, we have O2 and O6 planes, and the allowed fluxes is the Romance mass, the NS field, and the RRF4. And this can be expanded on the basis of the fundamental form, and here psi is the dual of this basis. So the integrated Jack identity here, if we integrate in the compact space, we can see that the fluxes of the fields here are bounded by the charge of O2. Why do we care about that? We'll see later. First of all, because of the flux quantization. I mean that you can have a supergravity, find some vacua from a supergravity and be like okay to look consistent. But when you want to contact it with string theory, you have to quantize these fluxes here, and also we'll see that there are some problems with scale separation. So we perform dimensional reduction from 10 dimensions, and we get the following energy potential here. I have modified a bit this term that corresponds to the O6 plane, but if we forget the Romance mass and the O6, we see that the first part is a total square. So the solution is a Minkowski vacuum, and actually you can see that it probably has flat directions. So as I said, the effective field theory is a 3D supergravity with 2 real supercharges, and here you can see the kinetic terms. Here with X and Y, we denote a combination of the volume modulus and the dilaton field. So we go and guess what is the superpotential that gives us this potential that we got from dimensional reduction. And we can see here that this term, for example, corresponds to the Minkowski, which is actually no scale, Minkowski. And when we add the Romance mass, when we turn on the Romance mass, from cross terms, we also get a contribution, this contribution here, which actually is the O6 plane. Okay, so we have found the superpotential, and now we can see what is the effect of the rest of the terms here in the potential, like the Romance mass and the O6 planes. So we perform length variation, and here, sorry, we have changed again the notation. So R and tau, you can see it from the line element here. It corresponds to the modulus of the internal space, and tau here is a combination of the modulus again and the dilaton. So we perform the variation of the potential that we have, and we can see that we can have a fully stabilized vacuum like the Volcidol. What we want to do is, if it's possible, if you have any indication for scale separation, and by this we mean the decoupling of the Kaluza-Klein scale and the radius of the ADS3. To do that, we go to the potential and perform a scaling analysis. So we require all the terms to have the same scaling in order to see the contribution of each term. And we see that the only term from the fluxes that can take large values, and it affects, of course, the separation of scales, is the RR field, the F4. But we saw before that the fluxes, due to the Bianchi identity, the number cancellation can be bounded. So we want to unbound this, and in order to do that, we treat the Bianchi identity differently. So we perform a O2D2 cancellation. Here we perform a O2D2 cancellation, and requiring the H3 wedge F4 should be here to be 0. So this way the flux is unbounded. And we have an example for that. We perform the supersymmetric equation, and we find some solutions for the isotropic tori, which means like the SI moduli are stabilized at the same point. So we find the scale separation, and we see that for the scale separation, the responsible flux indeed is the flux of the F4. This is the vacuum solution, and we have also positive masses, and of course we are at the weak coupling and large volume regime. But here we have not considered yet flux quantization. You can see it from the values here. So what we want to do now is to try and see if we can have the Sitter vacuum. So we start from the potential from our previous setup, but now we add the branes, which actually are associative breaking terms, and then we require the potential to have some energy epsilon, and also these critical points here. The first step that we do is to check the masses, and we see that for large energies here, there is a possibility for a tachyon to appear, and these masses here correspond to the universal the universal part. I mean the universal modulus, so the dilaton and the volume modulus, where like the masses for the shape moduli of the internal space, they don't look to have a tachyon. An interpretation for this one can be that the SI moduli are still stabilized at their supersymmetric positions, because what we did is that we took the potential that we found before, we add under two branes, and we require to have like a positive energy, and this will give us strong constraints on the fluxes. Okay. So now we want to check the flux quantization and also the critical points of the vacuum, and we see that the critical points put really strong constraints on the number of the branes and the fluxes. So we treat the tadpole conditions considering also the flux quantization, and here 16 corresponds to the number of 06 planes, and it seems that there is no problem with the first condition if we take W, which W is this fraction here to be 1/3, but we have a problem with this tadpole condition here, because when we extremize the potential in terms of Y and take the limit to small energies, we see that this term here is not an integer. And since we have performed a flux quantization, we want the number of either two branes to be an integer number. So somehow we want to fix this term here. And this can be done if we consider added two branes with a warping effect. Since the warping effect will add a contribution to the potential, here A is the contribution, and then this contribution will appear as a number here. So we figure the number in order to get an integer number for the number of added two branes. We have also an example here with integer numbers for fluxes in order to be compatible with flux quantization. And what we get is indeed a large volume and weak coupling and positive masses, and also the vacuum energy is positive. So everything looks okay until now, but there is another problem that is that leads to metastability of the de Sitter vacuum, and it has to do with the brane flux decay. So our relation doesn't satisfy. Sorry, our number of anti-branes, the flux do not satisfy this relation here. So there is like possibility for our vacuum to decay, be metastable. This can be cured if somebody see the analytic expression of this form here. This can be cured if we increase the energy, but if we increase the energy as we saw in the beginning, we can have tachyons. So it seems that we cannot avoid that, but we can go to internal spaces with that allow large numbers of quanta and satisfy this inequality here. So I have like 2 or 3 minutes probably. Two words about the type 2B results. Of course, the spectrum is different. Of course, the planes and the local objects that we can consider are different. And in this case, we want to have like a curved internal space. So we perform a surge Svark twisting on the torus. Also, you can see here from the background flux that are allowed that the H3 is not allowed. So we have to cancel the tadpole differently. But this is not a problem because since we are in the because the Fi, basically the basis of the fundamental 3 form, which actually the F3 is expanded on, is not 0, the derivative on it. So we can cancel the Bianchi identity differently. And again, we can perform a dimension reduction and find the potential as well as the swap potential. And we can see that the presence of the torsion classes that appear due to the curved background are crucial, because when they vanish, we don't have the contribution of O2 of all 5 planes. And I will stop here, like in this slide. I just want to say a few things about smearing here, because you remember that we treated the local objects differently. We considered, instead of in the localized direction, we put some smooth functions. So we have found the superpotential. We checked the supersymmetric conditions where it vanishes, and this is our solutions. And we are at type 2B theory, basically in type 1, sorry, since we also consider O9 and we can consider O9 and D9 local objects. And Dalianis et al. Have found the same solution here, but from another theory, from heterotic theory, and they didn't consider orientifolds. And from an S duality, we can see that we can go from heterotic to type 1 and compare our results, and they are the same. And the point here is that we have used smearing approximation, and people don't trust it. But here we see that we are in a regime that it gives the correct vacuum conditions, and this probably happens because our internal manifold is curved. So let me conclude. What we did is we searched for 3D vacua in type 2A, in type B, with Ricci flat internal space and non-Ricci flat internal space. We found supersymmetric ADS solutions. We canceled the tadpole properly. And we also saw that we can get probably a de Sitter that is metastable, but we have to check for more general spaces in order to see if we can save it. And yes, we also saw that in internal space, probably the smooth approximation can contain the information and give you the correct result, as we saw from the S duality with De Rosa. That's all.
Many thanks for your nice, clear talk. Interesting talk. Questions? As I said, it was very clear, so presumably there are no more questions. Outside questions? Gregory? No. So, there are no more questions. We thank the speaker again. So the last speaker of our morning session is Georgios Karagiannis, and he talks about higher Buscher rules in gauge theory and gravity. Please.
Yes, thank you very much. I would also like to thank the organizers for giving me the opportunity to talk to this very nice conference once again in Corfu. I'm going to talk about higher Buscher rules in gauge theory and gravity, and it's based on a recent paper that we wrote with Thanasis Strakidis and Taras Ronspar, as well as in some work in progress, hopefully to appear soon. So my main motivation will start by T-duality, which is, of course, one of the most well-studied dualities in physics. And in its simplest form, it indicates that basically you can have two distinct two-dimensional compact scalars propagating on circles of radii r and 1 over r. And when quantized, they will carry the same energy. And as such, it has a geometric interpretation simply because it acts on the target space, which is the original circle, by inverting its radius. And as a second step, one can consider the string sigma model, for instance, which contains multiple two-dimensional scalars. And then the action of T-duality on the string backgrounds is going to be given by the famous Buscher rules. So this is about T-duality, but then, of course, there are also strong weak dualities. And the simplest example of these dualities is the electromagnetic duality, which basically relates two distinct Maxwell theories with inverse couplings, and also in a more different form. If you also include the electromagnetic theta term, then these couplings E and 1 over E become the complex couplings tau, which I'm going to discuss. And naturally, we had this question. So what if we consider a four-dimensional sigma model-like theory for multiple abelian one-forms, just to somehow mimic the procedure of constructing the string sigma model for the scalars? Then how will then electromagnetic duality act on the background fields? And to take it a step further, one can even ask such a question about linear S gravity, because we know that electromagnetic duality exists also in linear S gravity. And more generally, like the main question we were motivated by was how stringy are the Buscher rules. So I'm going to elaborate that the answer to this question is negative. I mean that they're not stringy at all. So let me begin by reviewing the most well-known case, which is the two-dimensional scalars and the string sigma model. This is given by, let's say, D compact scalars, XM, and this is the action here. So G and B are symmetric and antisymmetric background fields on sigma 2. Sigma 2 is the string worldsheet. And these ellipses here denote higher order terms, like, for instance, the dilaton coupling. And XM can be seen as the components of the sigma model map X from the sigma 2 to some d-dimensional target space manifold, which I call purely MD. So here in this setting, the vanishing of the beta functions of the string sigma model implies the Einstein equations for the low energy field theory of the target space. And this leads to the string miracle, in quotation marks, which is simply the fact that the string target space is meaningful itself as a physical space-time, with G and B being the dynamical Riemannian metric and Kalb-Ramond field. And just to make two very fast comments here. So simply because of the fact that dx, which dx vanishes identically, we can see that a single two-dimensional scalar has a vanishing theta term. And I call it a theta term because in electromagnetism, the theta term is just theta dA, which dA. So two-dimensional scalars do not have theta terms. I mean, a single one, but it's amusing to think of this term here, which I write here, to see it as generalized the term that mixes the scalar fields. So now one can assume that the target space has a number of isometries, let's say S of them, generated by some Killing vectors. So these are the invariance conditions on the background fields. And then we can split the scalar fields into some spectator fields, which I call XM, small m, and then some other fields, S of them, which I call X alpha. And in fact, one can dualize all of these extra fields. And just to show a little bit one way in which one can perform the dualization, we can consider this parent action here. So as you can see, this is an action that contains the spectator fields, XM, as well as two auxiliary fields. So X tilde is a scalar and F is a one form. And in fact, in terms of the spectator fields, this is exactly the same action as the sigma model I showed earlier, but it has some terms here that contain F and X tilde. And basically, F and X tilde are auxiliary fields that can be integrated out. And upon integrating them out, one obtains the two dual second-order theories containing X, which is the original scalar, let's say, and X tilde, which is its dual. So to do it very fastly, one can say that we can integrate out X tilde through its equation of motion, which basically forces the Bianchi identity on F. And then locally, this means that F should be actually D of a scalar. And this scalar is what we call the original scalar, the original field. On the other hand, one can integrate out F through its equation of motion, which is this one here. This is also called the duality relation in the literature. And then plugging this duality relation back into the parent action will give us an action like the dual action, which will also be second order in derivatives also for X tilde. And the interesting thing is that the background fields of the dual theories are related by these expressions here, these rules. And these are in fact the Buscher rules, if you can call them like that, if you integrate, if you dualize along one direction. But in fact, as I said, if there are S isometries, one can dualize along all the directions, X alpha. And then the action of T-duality will be given by the famous Buscher rules, which I write here in terms of the generalized metric A equals G plus B. And in fact, these Buscher rules are, it's known that they're associated to the orthogonal group ODD. Now, let me try to consider a little bit more different perspective here, and construct this sigma model-like theory which contains d abelian one-forms on the Minkowski space of 4 dimensions. And here, in this case, G and B are both symmetric background fields on sigma 4, and can be in general functions of scalar fields as well as gauge invariant combinations involving the field strengths of the scalars. And in fact, one can think of this as a sigma model for a map A from the tangent bundle of sigma 4 to some appropriate graded d-dimensional target space. And I say graded because it's clear that it should be equipped with degree 1 coordinates. So here, of course, the comment in analogy with 2D scalar case is that a single 4-dimensional abelian one-form has a theta term, since dA squared does not vanish identically. And now, here we have electromagnetic duality. So we can assume that the background fields G and B do not depend explicitly on a number of distinct field strengths. Let's say that, again, this number is S. And in this case, the theory will be linear in the fields A alpha and possibly non-linear in the spectator fields. And in fact, the spectator fields could even be non-abelian for the purposes that I would like to discuss. It doesn't play any role. And one can consider again a parent action and dualize all of these fields. And they will find that the electromagnetic duality acts on the background fields in this way here, where I have used the complex coupling tau defined like this. And you can actually see that these rules are very similar to the ordinary Buscher rules, the ODD ones, in terms of the generalized metric. But there are some extra minuses, which basically force these rules to be related to the symplectic group, SP2D. And then, in general, the background fields can depend on any of the field strengths. And in fact, in this case, one can still dualize the respective fields, provided that the corresponding nonlinear theory is invariant under the abelian electromagnetic duality. And in fact, we are currently working on a systematic way to dualize collectively all such nonlinear theories at the offset level using a parent action approach. And just to give some kind of famous examples of such nonlinear theories that are duality invariant, or the abelian duality, are the Born-Infeld theory and the very recently proposed Modmax theory by these gentlemen here, which, just to say what it is, it's the unique nonlinear extension of Maxwell's theory that preserves both duality under electromagnetic, that is duality invariant and conformal. So they are given by this kind of actions here, where K is the Maxwell kinetic term, F mu nu, F mu nu, and then T is the theta term, the electromagnetic theta term. So in fact, these two actions can be written in a non-unique way as the sigma models that I wrote earlier, with very specific couplings that are field dependent. So G and B here for Born-Infeld will take this form, and for Modmax you can even write it without including a B field. This was just to show that the nonlinear, that the sigma model-like theory we consider was actually quite general. You can write lots of theories like that, and without repeating lots of stuff, just to mention that you can directly generalize this dualization procedure with the parent action to theories of this form here, which contain d abelian p forms on self-dual dimensions. And then, of course, G is always symmetric, while B is either antisymmetric for even P or symmetric for odd P. And you will eventually find that there exist two sets of Buscher rules, either the ordinary ones for even P, or the symplectic higher ones for odd P. And now there is this next step that one can take, and it regards linearized gravity. So it's of course well known that it exhibits electromagnetic duality, and this is mainly because in absence of sources, the Einstein equation, the Bianchi identities on the linearized Riemann tensor, which are this one here, are also satisfied by the Hodge dual tensor by definition. But in fact, however, it was suggested 20 years ago by Chris Hall that this duality relation here may be extended to this one, where G square is a dimensionless constant. It should not be confused with the dimensional full G Newton. In fact, it can be absorbed into G Newton. And here theta, this theta parameter here, is a constant dimensionless gravitational theta angle. The analog, the gravitational analog of the electromagnetic theta angle. And in fact, this gravitational duality relation really looks formally analogous to this one here, which is obtained from dualizing classical electromagnetism, so Maxwell-Lagrangian, with the addition of the theta term. And in fact, this theory here can be written like that, of course, in terms of the electromagnetic fields. And it's then natural to extend to expect that the extended gravitational duality relation proposed by Hall should be obtained by dualizing a linearized gravitational theory of this form. So we have the standard linearized Einstein-Hilbert term, and then we should add the topological gravitational analog of the electromagnetic theta term. So the natural question is, how can we find what is this term here? And then I'm not going to go through details because they're not very important. Just to mention that we used a formal analogy between electromagnetism and linearized gravity, which is called gravity-electromagnetism. So basically, you just define some potentials, phi g and ag, in terms of the components of the linearized metric. And in the same way as in electromagnetism, you can define some fields, so EG and BG. In fact, EG is the standard Newtonian potential, while BG is what they call the gravitomagnetic potential. And in any case, if you define these fields here, E and B, then you can actually see that in the de Donter gauge, the linearized Einstein-Hilbert action can be written in this way here, in this form, which really resembles the E square minus B square electromagnetic Maxwell-Lagrangian. And this gives us a hint. So how about adding a term like that, theta Eg dot Bg? So the really direct analog of the electromagnetic one. And in fact, this term is a total derivative, and its nonlinear origin comes from a well-known four-form, which is called the Nie-Yang four-form. It's written as a sum of a torsion square term and this term here, which is usually called the Holst term. And in fact, it is a total derivative term and a topological invariant. And it's kind of normal if somebody is not familiar with this term, mainly because it vanishes identically in general relativity. Simply because GR is based on a torsionless connection. But the Nie-Yang term actually can exist and has a number of applications in gravitational theories based on torsional connections, like Einstein-Cartan theory, for example. And just to briefly mention some other applications of this term, in this linearized term, well, it can actually lead to modifications in the Newtonian potential if you couple it to the original linearized Einstein-Hilbert action. Then, in the same way as the gravitational Chern-Simons term, which is the R-square term, it predicts corrections to physical effects like the lens steering effect or the gyroscopic precession. And in fact, maybe even more interestingly, it has been used excessively in condensed matter physics, for example, to measure the gravitational response of topological materials. So this term has a number of interesting applications. And like for this gravitational duality that I am trying to show, one can use the parent action approach. And in fact, one can write down this action here in terms of two independent fields, F and lambda, which have these index symmetries. And of course, again, the dual second-order theories can be obtained by integrating out once F and then lambda. So without this red term here, this was exactly the parent action considered by Peter West, again 20 years ago. And it was shown that it actually relates to linearized Einstein fiber theories with inverse dimensionless couplings. So it naturally leads to the standard duality relation that I showed earlier, this one here. And in our work, we actually showed that if you include this particular red term, then you obtain the extended duality relation predicted by Chris Hall. So, in fact, the two dual theories will be linearized Einstein Hilbert theories equipped with gravitational theta terms, and the dual couplings will be given in terms of the original ones like that here. Or if you prefer, you can define again the complex metric coupling, like that, and then you can actually see that tau tilde is -1/τ. And as I said, the on-cell relation that you obtain is precisely the one predicted on-cell. Now, just to mention a little bit briefly also what is the double duality and what is the relation of the theta term with double duality. Thank you. Standard electromagnetic duality results by force dualizing like the first two indices of the Riemann tensor. But instead, one could dualize both slots of the Riemann tensor, like that. And this actually leads to an algebraic relation between the double dual Riemann tensor, R prime, and the original Riemann tensor. And as shown also very recently, this duality relation here, this on-cell relation, forces the actual gauge fields, which are the linearized gravitons, to also be algebraically related on cell, up to gauge transformations, which are basically linearized diffeomorphisms. And this leads to the conclusion that the double dual picture of linearized gravity is not an independent picture. Of course, there were also indications about that from earlier work of Hall, because he showed that linearized gravity does not admit three independent sources. So there can only be two independent sources in linearized gravity. I mean, either the electric and magnetic one, or the electric and the double magnetic, or the magnetic and the double magnetic. And however, in the presence of the gravitational theta term that I discussed, the on-cell double duality relation predicted by Hall was this one here, and this is exactly what you obtain at the off-cell level, like using the off-cell approach from our parent action. And it should be quite obvious from this relation here that the double dual linearized graviton and the linearized graviton are not related algebraically on cell, because you can see that here we have an extra term, this term here, which was absent in this duality relation here. And this term here forces the dual fields to not be algebraically related on cell. And in fact, this leads to the observation that double duality, the double dual description should be independent if one includes the theta term inside. It's quite interesting, I think. And just to generalize a little bit these discussions a little bit more. So in the sigma model spirit of the p-forms that we did earlier, four-dimensional linearized gravity actions with theta term can be generalized to accommodate an arbitrary number of linearized gravitons. So you just write down a sigma model like theory with couplings GMN and BMN, and M and N can take arbitrary values. So you can consider arbitrary number of fields. And in fact, we used the graded geometric formalism, which was developed in 2019, to examine the duality rules for such theories, and also for theories containing more general mixed symmetry tensor gauge fields of Young tableau types p,1 in 2p+2 self-dual dimensions. And what we found was that just like the case of p-forms, if p is even, then the relevant coupling is the generalized metric, and it transforms under duality through the ordinary ODD Buscher rules. And when P is odd, then the relevant coupling is the complex coupling, tau, and it transforms under duality through the higher symplectic Buscher rules. And as a final remark, I would like to mention that G and B, usually we assume that they depend on scalar fields, in which case we find indeed the non-compact duality groups here, ODD and SP2D. But in fact, if they do not depend on scalars, then these non-compact duality groups should restrict to their maximal compact subgroups, which are OD and U to the D. And let me briefly mention some work in progress and some future directions in collaboration with Thanas and Taras. As I said, we are working on developing a systematic way to dualize at the off-cell level nonlinear theories, which are invariant under some abelian duality. Then we are also interested that we're working on identifying the Hopf anomalies and their matching between these dual theories, as well as finding the corresponding anomaly polynomials. And finally, we wish to investigate the notion of an isometry on these graded target spaces using the invariance conditions posed on the background field by the generalized global symmetries of the sigma models. And with that, I would like to conclude. Thanks for your attention.
Thank you very much for your nice talk, interesting talk. Questions? Very good.
Thank you for this nice talk. So in string theory, we also have the dilaton, which is typically has to be included in the duality. How is there a way to include that also for the higher?
We haven't thought about. I mean, we haven't considered it. We just ignore the higher order terms, whatever they can be. But it would be interesting, actually. Thanks. Thanks.
Are there more questions? All right, so thank you again, and also thanks to all the speakers of this morning.